Welcome back, everybody. It's another past midnight special for COGS118A. Um, the cat is asleep right there. The child is asleep over there. And, well, you and I, lucky viewer, we get to talk about machine learning and specifically about error metrics, about how we're going to measure performance once we actually create a bunch of models and need to compare them against each other. Well, I think we're going to have a lot of fun tonight. This lecture might be a smidgen shorter than most of the others, but I'm sure nobody's going to basically complain about being let out of the lecture hall early, right? Now, away we go. So first off, a couple of bits of business. As you all should know by now, we've turned in assignment 1, and assignment 2 is out. It's on Canvas. It's due at just before midnight on October 23rd. There have been a few bits of confusion in the Piazza about various things related to the course. I do want to point out that if you ever have a question about what is true, when is a test, what is the official policy for something, etc., you can always take a look in Canvas. In the logistics module, you can see the syllabus for this course. And just a reminder, this syllabus is kind of a living document. It's going to be updated from time to time. There will be more suggested readings for each week, so on and so forth. Certainly, I only filled in about a good chunk of the schedule was only filled in detail up to the first midterm, and now that we're approaching that time, it is definitely time for me to update that. Now, one of the things that I did mess up in the syllabus is that I forgot to include a late policy, and that has already come up here with assignment 1. So I'm saying that what we're going to do is 10% off every day late. You can't get worse than 50% off the grade, and you cannot turn in an assignment or a homework more than 1 week late. Also, along that lines, why 1 week late is the max? Well, it's because we have a deadline of getting you your grades back no later than 1 week after you have handed them in. I'm sure you all will appreciate actually getting your grades back in a reasonable number of days. So that's why we have a maximum 1 week on the late policy. Also, the midterm is coming October 1st, or sorry, it is October 30th, and you will get a little bit of a break in the homework schedule. So we have assignment 2 right now, but the week after assignment 2 is due, there won't be a new assignment because that will be midterm week. And so that will give you a break to really focus in on studying. So along the lines of the midterm, there is a Google poll here, link in the PDF. For those of you watching this on Canvas, there should be a pop-up thing right about now that will let you actually click through and get to the form. For those of you watching on YouTube, I'll put the link in the notes there, okay? So please participate in this poll so we can figure out a little bit about what your needs and capabilities are. We are still trying to figure out exactly the right way to administer this test. I'm vaguely going to say that our 3 main things are: we can use Canvas tools, we can use Jupyter Notebook distributed to everybody, or we can use a paper method. And each of them have pain and suffering attached to it compared to our regular routine. And yeah, I just want to know what's the problems that you can't deal with. Okay, away we go to the fun stuff. So error metrics, yeah. Because we want to know how good is good. Because once we have a machine learning algorithm, we need to know not just how good is it, But how is it compared to other possible machine learning algorithms we could use to do the same problem, right? So when you want to know how good something is, we keep talking about, so far, we've talked about the loss function itself. We've talked about the error on the training set. We've talked about the error on the test set. But, and so fundamentally, we've said those are the loss function, right? That is the thing we are trying to minimize is often how we are defining it. But it doesn't have to be that way. You can measure error on a training or a test set with something other than the loss function. Why would you do that? Well, the loss function is a natural thing because we're saying that's our definition of what good performance is, so it makes sense to use your loss function. But the thing is different machine learning algorithms have different loss functions. The loss function is inherent to the way in which it learns. So that means if you're trying to compare machine learning algorithm 1 with a particular loss function with machine learning algorithm 2 with a different loss function, you need something else, right? Because they don't share a loss function. You may also, besides that, want to get some sense of a different aspect of performance than the one you've tried to optimize, okay? These are things that will make more sense to you as you've played games with various things, but I think that you can see immediately that just because you want to compare models with different loss functions, you definitely need some separate way of doing that. Now, there are many, many ways to skin a cat. Sorry, Magic. He didn't wake up anyway. There are many different ways to measure something. Oftentimes, these measurements are only applicable to one of the broad kinds of machine learning problems. So it's only applicable to a classification problem, birds or not birds, or it's only applicable to a regression problem. You know, we want to fit the line. Even within those broad categories, there are different metrics, and they're after different aspects of performance. What you're seeing here is a list of the current scikit-learn metrics that can be used. Each one of them is an interesting question and case, something that you should study fully before using it. One thing that I am not in favor of that I see people doing all the time is they just go, oh, well, Bob used F1, that must be the thing to use. All right, well, do you know what F1 is? Do you know why you use it? There's particular times in which F1 is an excellent metric to be concerned about with classification problems. But if you don't know the theoretical considerations, you will misapply things. So don't just read the documents in a software package and then just assume you know enough about what you're applying. It is important to actually understand the math behind things. All right, well, we're going to do a quick tour of a few things here. What are we going to talk about today? We'll talk about accuracy scores and precision recall. We'll talk about the receiver operating characteristics, area under the curve. Oops, not the OVR version, but the regular version, whatever. And we'll talk about mean absolute error, mean squared error, and R squared. So, just a quick tour and getting you into at least a basic understanding of what these things are. All right. So, error metrics. Having some sort of benchmark to understand and compare algorithm 1 versus algorithm 2 is really one of the key elements both of how we get stuff done and in general how the field of machine learning as a research field is developing by leaps and bounds. People are super concerned with what algorithm does best on a given data set. There are these standard benchmark data sets that people are using to compare image classification, is what we'll talk about here in a second, right? And having both a data set that everybody tries their own algorithms on and an evaluation metric to compare across algorithms what is the best one to do this job. Those are absolutely necessary, and that's how you see these thousands of machine learning papers published every year cranking out, hey, look at my algorithm. It does this good on the MNIST data set, right? Okay. So being able to make sure that you can faithfully compare things, that you can represent accurately the performance of a new algorithm, and do it in such a way, importantly, that other people can reproduce your result and check it out for themselves and do it in their own hand and see that what you said isn't a lie. These are super important to the field of machine learning. Okay? So we have to establish objective functions to optimize machine learning algorithms. And the whole idea behind that, we've already kind of discussed. Loss functions. Loss functions are a matter of measuring the error, plus maybe a regularization component to try to make sure that your model doesn't get too complex, right? Remember, we use like an L2 on the weights to squish the weights to keep them from getting too big so we don't overfit the data. All right, well, what about this bit here, right? The benchmarks. We need to tell you a little bit about how benchmarks work because, like I said, it's the way machine learning research gets done. It's what you're going to be doing for your research project. So there are, I would say, dozens of popular benchmark data sets and probably hundreds more that are commonly used. So here is one repository of benchmark results, papers with code. Paperswithcode.com. It's actually something very fun. Go take a look. So in papers.com, there is essentially a leaderboard. Who's winning for various different data sets. Imagenet is a, as you might guess, computer vision data set that people use. It has thousands and thousands of images. And the task is, can you correctly classify each one of these images by different semantic tags? Okay? And what you can see here is that over time, 2011 to 2020, the top level of performance on Imagenet has gotten better and better. And actually, more to the point, more and more papers have also been published, as you'll notice, as we get into this decade, and especially, sorry, not this decade. I don't even know where we are in the calendar anymore. But as we get in the last 5 years, you have loads more of these than in the first 5 years of Imagenet. So, right, what does Imagenet look like? Right, well, we can say that, actually, I should say, what do the metrics look like, right? So this accuracy score, it is what, for every one of these thousands of images, what is the label that an algorithm says this should be? And if the label you pick, the best label, is the correct one, then you have 100% accuracy. And if you only get 80% of them right, the way roughly we get right now, you're only labeling 80% of them correct. It is the inverse of the classification error that we keep talking about. All right. So what does Imagenet look like? Well, the data set is these thousands of images, and they're labeled according to a semantic hierarchy. So if we go into all of Imagenet, there's plants and geology and natural objects, and then there's sport. And inside the categories of sport, there's contact sport. And inside the categories of contact sport, there's football. And inside the category of football, there is, as I like to call it, hand egg, American football, and real football, the soccer association football. Like, you know, in case you didn't know, soccer is a contraction of association football, associationer. Well, that was super exciting. And inside that category, you would have images that might look like this. Very wildly different. No, difficult images without any particular attempt to keep lighting the same, or to make sure that it's zoomed in on the action and the important topic. Okay, stuff like that. All right, so let's go to the problem. It is, as we always have, we have a training set of n samples and an input which has m features. And we are trying to classify. We're trying to say this is football or it is not football. Okay? Or in this case, we have a diagnostic test, some sort of medical test, and it measures whatever we see in the blood, something. And we want to say, is this person sick? Sick plus, yes. They are positively sick, or they are not sick. They are negative. Okay? Positive test, negative test. So what we're going to do is we're going to train a classifier. It's going to produce outputs, and the outputs it produces are going to be a function of the inputs and the weights, the parameters. Okay, and all those outputs are going to be either -1s or +1s. We're going to learn that W. We're going to learn it by minimizing a misclassification rate, right? So misclassification rate, if the output of the algorithm is not the desired target, the Y value, the true labels, then we're going to add 1 to the misclassification error. And we're going to sum up over all of our data and normalize so that we get the the ratio of misclassifications, right? So this is on the training set. This is the training set misclassification error. Okay, so graphically, we have a bunch of sickies that are labeled in the blue, and in the yellow they are sick, and in the blue they are not sick. And we've drawn some line that we're optimizing to find those parameters that best reduce this misclassification error. So let's say here that we have 3 wrong answers out of 10. So that is the training error. Okay. Now, of course, we don't care about the training error in terms of performance. We want to know what it does in testing set. Okay. So the testing set has Q samples. Other than that, the rest of this remains the same. The same kinds of inputs, this parameter that we already learned. So we get new data. Okay. We run the same metric, right? Misclassification error. But this time it's over the Q samples of the testing set, and we get a new misclassification error, which is 4 misclassified, okay, out of 11, and that's that ratio. So misclassification rate, right? So if we want to compare algorithm performance, why don't we just use the misclassification rate? Well, as we've already kind of said, there can be reasons like you want to compare 2 algorithms that have different loss functions, right? One of them doesn't use misclassification rate. So we may need to do that. But also, this whole setup only really works when we have the same number of classes positive as negative, okay? When your sickies over here, right, this is the positive y = 1, and you're not sick, this would be, actually that should be -1, right? So, and you're not sick over there, have very different ratios, then this is not an accurate view of metric of performance. Okay? What does that mean? Well, so if we have the number of negatives, number of positives, So for example, if we have 1,000 negative samples, right, and 1 positive, there's 1,000 well people and 1 sick person. We can trivially classify every input sample as negative. We can just make a dumb classifier that doesn't care about the data. It just says negative, you're negative, you're negative, you're negative, and it's never going to say anything else. Well, how bad is it going to do by misclassification rate? That's pretty good. That's, a very, very good classification error rate. So, well, obviously, it's a dumb algorithm that we've invented, and it's not what we want, okay? So just FYI, right, what are we talking about here? Well, I mean, most diseases are rare, including our very own special COVID-19. So right now, my estimation, this is my stuff. So an epidemiologist, a real one, might have a slightly different take on it, but it's not going to be an order of magnitude off. And right now, we're around 1 out of 1,000 in terms of how many people in San Diego County right now are sick with COVID-19. So, this is relevant, right? Especially in the medical field. Diseases are rare, almost by definition. So if we're looking for diagnosing a disease, we're going to be in this situation almost always. So the way to go after this instead is to try to separate out the different kinds of mistakes we can make. So if we have actual reality over here, somebody is got a condition, somebody doesn't have a condition. And we have what our algorithm is predicting, that they do have the condition or don't have the condition. That gives us a logic table, right? And in this logic table, we have various different kinds of truths and errors. So if you actually have the condition and we tell you you don't, that's called a false negative. Okay? We tell the pregnant lady she's not pregnant. We tell the person who is sick with COVID that they don't have COVID. Okay? Another kind of error is the false positive. That's when they actually do not have the condition. They are not pregnant, but we tell them they are. Or they don't have COVID, and we tell them that they are sick with COVID. Well, we tell them that they tested positive for the virus. They can pretty much tell whether they're sick or not. So false positive errors and false negative errors can also be known as type 1 and type 2 errors. Don't worry too much about that. This is not a statistics class, okay? But you will hear these terms throughout your career. And I just want to make sure that you understand they're all the same thing. Now, if they're actually negative and we tell them they're negative, or they're actually positive and we tell them they're positive, those are good things, not errors. All right. So, to recap, we have truth and our predictions, right? And we're going to talk about something called the true positive rate. The true positive rate is the probability that you're going to classify this person as positive given that they are actually positive. Classify them as pregnant given that they are actually pregnant. And maybe you can hear the cat who wants to go out right now. No, Magic, you're not pregnant. Pardon me. Better that than to listen to the meowing. Right, so there's our true positive rate. You will also see this called sensitivity or recall. Why? Why in God's name do we have so many different vocabulary things to learn? Well, all this stuff has been developed, the math has been developed multiple times in different fields of study. And in one field of study, they called it the true positive rate. And in another field of study, they called it sensitivity. And in a third field of study, they called the same math recall. And I'm so sorry for you, but we all have to learn to deal with it because different people writing about this stuff will use different terminology. At any rate, that's the worst of the lot, thankfully. Okay, we're also interested in the false positive rate, which is the probability that we classify you as pregnant when you're actually a man and are not pregnant. Okay? So this is a good thing. True positivity rate and false positivity rate is a bad thing. You want this one to be low, you want this one to be high. Okay? Likewise, true negative rate is probability that we're going to classify it as you are not pregnant, given that you are not pregnant. So that's also called specificity. Okay, so sensitivity, think of it as the true positive rate. Think of sensitivity as how sensitive are you to pick up the problem? How sensitive is our test to pick up a pregnancy? How sensitive is our test to pick up COVID and correctly classify COVID patients as COVID positive? Okay. The true negative rate with its specificity is kind of the, not quite the inverse, but it is that we want to see how specific are we. If something is a negative, are we correctly calling it a negative? Okay, so we want those things to be high, the truth things, and we want the errors, the false positive rate and the false negative rate, to be low. And the only one we haven't done is the false negative rate, and it's the probability that we classify you as not being pregnant when you truly are. Okay? So, let's go through a quick example on how to calculate it. This is the same stuff. So we have the same problem. And for each person in the data set, we have their features that we can use some sort of blood measurement to measure. Let's say that we're going to try to get whether they are truly sick or not sick. So this person is not sick. This person is also not sick. This person is sick. This person is not sick. This is the truth value, right? This is the actual truth of the matter. Okay, so we have 100 of these things. Now our classifier comes through, takes those blood measurements, right, and says this not sick person is actually not sick. Okay, this not sick person, oh, we've classified them as sick. That's a mistake. This sick person we correctly classify as sick, and so on. Okay, how do we say how bad is it? Well, one of the easiest ways is the confusion matrix. So scikit-learn provides you with a confusion matrix if you would like to go investigate that. What is it? Well, it is simply this table that we've just been looking at, filled in, right? So this person being not sick and classified as not sick, we put a tick mark here for them, okay? So this person is not sick and we classified as them as sick, and so we put a tick mark in that box for them, which is exactly what we just talked about. So we do that again and again. So as we go through all the people, we summarize up all the stuff, and in the end, we have something where we can just fill in numbers, the total number of samples that we got in all of these categories, and we can go ahead and add up the numbers. So these are all the people who are actually sick, the ones we got right and the ones we got wrong. And there's a total of 40 of them. Okay, these are all the people who are not sick, and we got most of them correctly classified. Okay, and this is the total, 50 plus 10. And likewise, you can add up across this way to see about your classifications versus reality. Okay, so we want to use this kind of a thing as a way to evaluate not just how successful are we, but where are we making mistakes. So I will briefly mention, although we're not there yet, that we've only been dealing with binary classification. You either are sick or you're not sick. There are more general classification problems, like are you one of 5 different kinds of sick? Okay, multi-class problems. Something could be a bird or a reptile or a mammal, right? So we can have 3 different classes we're trying to dump stuff into. So in those cases, the confusion matrix enables us to explore how systematically things in category A are confused with things in category B or C. And sometimes you will find that your classifier does really well at some parts of the problem and crud at other parts of the problem. Okay. But as I said, that's just kind of a preview. We're not there yet. All right. So this ugly thing I pulled straight from Wikipedia, and I guarantee you will be spending time with this entry on Wikipedia over the course of your machine learning career. Precision and recall is, like I was saying, it's one of the words for true positive and false positive rates. Okay, so we have our truth table in here, right? True positives and true negatives, false positives and false negatives. In this case, just because it's going to be confusing potentially, I want to mark out that our previous slides were rotated 90 degrees. Up here is the truth. Previously we'd had the truth over here, and now down here is our prediction from our algorithm. Okay, but the truth table is still the truth table, it's just transposed. All right, what are we saying here? Well, each one of these is, like we said in the confusion matrix, a number we can populate by counting up things that happen during training and testing. Okay, and we have things that we've already discussed, like the true positivity rate, which is composed of information coming out of this column, and that's why it's there in the little table. Okay, and the true positivity rate, again, is the number of true positives over the total number of positives. Okay, so I don't want to get bogged down in this, except to say there are a few things I want to call out. Okay, we typically care a great deal about false positive rate and false negative rate. Those are 2 metrics which are often compared, and especially in the context of, say, a medical test, where we have these highly unbalanced categories, where we have 1,000 well people for every sick people. These are ways in which we can compare and still deal with that unbalanced metric. Okay? Because what they are is, they are the rates of, given all the correct responses you could have made, how many incorrect ones did you? Okay. Another score to call out is this F1 score that I was talking about earlier. So remember that this is, what is it? This is recall, and this is precision. Okay? And precision and recall are combined into one overall score. We'll talk more about that in a bit. But maybe first we should talk about precision and recall, sensitivity and specificity. Okay? So again, these are things that appear in that matrix. These are jargons that it will help if you can actually just say it off the top of your head. What is sensitivity? Okay? If you can't just say it off the top of your head, always go look it up in these lovely little diagrams on Wikipedia. So this whole diagram, this diagram is got two parts. These are positives. Everything over here that what's relevant is a positive, an actual sick person, an actual pregnant person. Okay? And this over here are the negatives. So we divided down the middle here. Right? So this is a set diagram, a Venn diagram, right? And the stuff inside the circle is what your algorithm decided to say was positive. So this is the predicted positives. Okay? So everything that's on this part of the diagram is a true positive. Everything on this part of the diagram is a false positive. All the stuff out here are things that you did not pick up. So actually, let me do that in blue. All that are things that your algorithm did not predict as positive, even though it actually was. Okay? So sensitivity is a measure of how good are you at picking up all the possible sick people out there. Okay? It is the true positives over all the possible positives that you could have grabbed. Okay? And this again is a thing that you want the number to be higher on. Okay? Your specificity is how many negative elements did not get selected over the total number of negative elements. Okay. Guess who's back and knocking on the door? Magic promises that he will not interrupt us anymore. Right, Magic? All right. So, another way to measure these things is a little different. And again, some of this comes from different fields doing the same math, coming up with different jargon. So, precision is a measure of how many of the things you selected were actually positive. Okay, so it works a different way. So it works with the positives, true positives over all the things you selected. And recall is how many relevant items are selected. It's actually the same as sensitivity. Okay? So here they are compared against each other. These are jargon. There is immediately this is actually the same. Recall and sensitivity. Magic, stop clawing my leg. And yeah, so different combinations of these will give you different kinds of metrics. Okay. So once again, just to bring it all home, here is this great huge table. You will become very good friends with it. So let's do a quick little reminder. What we want here is that, oh, magic. All right, enjoy that. So what we want here is large true positives, we want large true negatives, and we want everything else to go away, especially everything that's feline. Magic, I'm going to lock you out if you can't settle down. I'm going to hurry along, both because we're running out of time, even though I thought this would not take very long, and because magic's annoying me. Okay, so I would like to see what you think of a given confusion matrix. Okay, so here we have a confusion matrix, which, we have the, hey, go away you. So we have most of our sick people are actually classified as sick. So 30 to 10, so 3/4. And most of our not sick people are correctly classified as not sick. Only a fifth, it's a sixth, so only like 16% are classified incorrectly on the not sick people. Okay? So which of these is actually true? Does this data set, is this algorithm and data set, does it come out to be high sensitivity, low specificity, high sensitivity, high specificity, low sensitivity, low specificity, or low sensitivity and high specificity? So I'll give you a second to think, work back through the jargon, maybe bring up the Wikipedia page right next to me. Okay, it is a high sensitivity, right? So we get almost all of the possible sick people picked up. And it has high specificity because we have very few false negatives. All right. So the true positive rate is 0.75, it's 3/4. Our false positive rate is, about 16%. Okay, and the specificity is 50 out of 60, right? Sorry, 50 out of 60. So it's 83% specific, right? You would say this is 83% specific, this test. Okay, and the false negative rate is 1/4. So this is a relatively good test. Magic, nobody wants you. Go away before something bad happens and I lose this recording. All right, so if we're going to compare models, then maybe we have a different model, a different kind of test that has a very different true positive and false positive rate. So this is the one we just went through, and this one is actually got true positive and false positive rates that are much more typical of a COVID-19 test. So a COVID-19 test, there's a relatively high problem with missing with the false positives. Okay, so true positive rate is only 63%. That means that we are misclassifying about 1/3 of healthy people. Sorry, about 1/3 of sick people are not being diagnosed as truly COVID positive. That's what I'm trying to say. Yeah, so about 1/3 of sick people are classified as COVID negative when they are actually COVID positive. On the other hand, we make almost no false positive errors. So almost every single person who is actually negative gets told that they are negative. So it's an interesting thing. One could be sick, but the swab, comes back from the swab test and it says you're not sick. Okay. One more thing to throw out there on your mind-blown evening. There is another bit of loveliness from the field of electrical engineering called the receiver operating characteristic. And as you might guess, it is about how radars whether or not they can accurately detect enemy aircraft coming in, right? The radar receiver operating characteristic is a measure of how good your radar receiver is at delineating between true positives and false positives, and true negatives and false negatives. Enemy airplanes or just a cloud. Or in our case, this same math, adopted with the same kind of 1947 terminology, now, and it lets us look at how good is the overall performance of a classifier, right? So you can easily figure this part. You can just intuitively figure out that if you made a test be really, really good at not having any false positives, at not telling well people that they were sick, then you might start to have a problem with false negatives, telling people who are truly sick that they are just fine. Okay? This is almost, in a sense, a trade-off, right? So look back over here, right? This one has a very low false positive rate, but its false negative rate is getting kind of high. Okay? This one is much more balanced. Well, what happens is, as we move back and forth, as we get more and more false positives, then we are, at that point, less likely to have any true positive problems. Okay? And likewise, if we get very few true positive problems, then we are more likely to have less false positives. All right. Again, take a moment, think about the fact that there's a trade-off here, that when you're very, very good at detecting something, you might be overly sensitive and get a fair number of false positives. Magic. Nobody wants you still. And stay off the mic because that really hurts people's ears. All right. So, important to note here is that what we're doing is we're combining into one measurement all of the false positive rate kind of stuff, right? All the different aspects of that truth table, okay? So what we're trying to do is we're going to say that as we go back and forth across this trade-off, the best classifier is one whose false positive rate stays very, very low until we get a huge true positive rate. This is the great model here, this blue, okay? As we get better and better at actually detecting all the incidents, all the COVID patients, only once we get very close to perfect do we start to come up with a lot of false alarms, okay? That's a great classifier. We know there's an inevitable trade-off in here, and perfection is running right through the corners, but we're never going to get there. Okay? Something which is still a decent model is going to slowly increase in false positive rate, going this way. As we get closer to 80%, we're already up to, like, say, 20% error on the false positive. And a crap model is one that's relatively flat here, where for every move that we make to increase our proper detection of sick COVID patients, we are causing more false positives. Okay? Chance performance is the diagonal line. Okay? And what you may figure out by now, because this says area under the curve here, AUC, is that by comparing the area under the curve, we can tell just how good something is, right? So this is the green area under the curve, and that's the red. The red curve has more area under it. It is a better classifier. As you twiddle the knobs back and forth, dealing with that trade-off in getting all the detections you need to make versus not having too many false positives, Okay, this red one does better than that green one. Okay, so we are just about at time. I was totally wrong about this being a fast lecture. Sorry about that. Magic didn't help. But I hope you're starting to get an idea. So classification is much harder in this respect than regression. Most regression metrics are a lot easier to understand, and there seems to be a lot less jargon around them. Probably the gold standard is R squared. Okay? R squared is simply a ratio of how much of the variance of your actual process is compared to how much the variance is in your predictions. Okay, and this is also called the coefficient of determination. So you put those two together into a ratio, and what happens with this number is when most of the variance in the system is explained by your predictions, then this value gets close to 1. Okay? When the variance in the system can't be explained by your predictive variable, by your x's, then this value goes towards 0 and even negative. Okay? So perfect prediction, where your predictive variable, your x value, can help you predict the y value perfectly, we get that r squared is equal to 1. And if it's just chance performance, then your r squared is equal to 0. And if you would actually do better than just guessing the mean y, if you would do worse than guessing the mean of the whole data set, that's when you get a negative r squared. All right? So it's a relatively simple measure. It is, I would say, the most common, especially in statistical regression. This is why we can kind of get a sense, because remember, it's also called explained variance. Okay, how much of the variance in the data is explained by that x variable? Okay, there are some problems with this. If you just keep adding more features to your model, more model complexity, it always increases r squared. So of course there's a penalized version of r squared called adjusted r squared that tries to penalize model complexity the same way that we talked about in ridge regression, where we have a weights penalty. Okay? But there are also some other common regression scores we've actually already discussed. Mean squared error and mean absolute error are relatively common ways. Okay? Well, that is all I had for you in terms of actual presentation. I do want to show you one other thing while we're on the topic of regression. Just very quickly. So r squared is also related to the correlation coefficient. And it can be quite amusing. So Pearson R is an r squared, right? This is kind of fun. You should definitely take an attempt at this yourself. There's a lovely little game called guessthecorrelation.com, and it has some wonderful, like, classic Nintendo or even earlier kind of stuff. I don't know if you can hear the sound effects. I know that this is not recording straight off the system sound, but they might be strong enough to come through on the mic. So, what is the correlation of these dots? Pretty small. I'm going to say it was a little higher than I thought it was. The true R was 0.26. All right. This one's pretty tight. Let's call that a 7. It was a 0.8. Let's call that a 0.6. Ooh, getting close. Poor. Maybe a 0.4. Nice. What do you think I should guess? Nice. All right, you get the point. I'm not going to play anymore, but you should, because it is a very big question. What does an R squared or a correlation, Pearson-R correlation, mean, right? What does it mean to have a good R squared? You notice like some relatively tight stuff there actually showed as, you know, not anywhere close to a 1, right? I don't know if we're going to get anything out of the random generator here. But when you see a really tight thing and it turns out it's only got a 0.7 on it, it can be quite surprising. So games like this can help develop your intuition about what these statistics mean. All right? At any rate, that's all I had for us today. I appreciate your attention. Magic appreciates your attention, and we'll chat with you all in office hours in the next lecture. Good luck with assignment 2. Bye.